So we'll continue with our discussions of the principles of reliable data transfer protocol. Last lecture we initiated with the development of this reliable data transfer protocol. We started with our assumptions that the network layer is reliable, which evidently is not, and then we started developing this protocol and see how would this protocol behave if the network layer is reliable. If you remember, this was the final state machine of our first version of the protocol, which we named as rdt 1. Today we'll make certain modifications to our assumptions and then see how would this particular protocol would behave if those assumptions are changed. Please refer to the previous lectures to understand the first version of RDT. Today we'll start with the modified assumption. So this was our first assumption. The assumption was that the network layer is reliable in the sense that there is no loss of packets and the data is transmitted without any error. Now let's make certain changes to this assumption. Today we'll assume that the network layer is not entirely reliable, but the network layer does not lose packets, but bit level errors can take place. And let's name this as RDT version 2. Let's understand what this assumption really means. This assumption means that if the sender is sending certain information to the other side, say the sender is sending these bits. So these bits are sent from a sender to a receiver. This assumption assumes that the network layer does not lose packet. That means what are the number of bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 bits are being transmitted. The network layer does not lose packets. That means that 17 bits will be received at the other end. There will be no loss of data, but some errors can take place in this data. That means this first one can become a 0, another 0 can become 1, another 0 can become 1, something like that. Some bit level errors may happen. That means the bits may get flipped, but the number of bits that is being transmitted from one side to the other side would not change. If I'm sending 100 bytes of data, 100 bytes of data will arrive at the other end, but some of the data can get corrupted in between. Where they can get corrupted? It can get corrupted in any place. In the sender itself, in the intermediate links, in the intermediate routers or switches, before it is arriving at the receiver. At any point, these errors can happen. So we'll see today how our protocol changes if this particular assumption is made. Now let's see what changes are required to be made to our protocol if we change our assumptions. In our first assumption, when the network layer was reliable, there was not much work to be done. The transport layer of the sender side simply takes data from the application layer and make packets and send to the other side. The other side waits for data from the network layer. If data arrives, if packet arrives, it simply extracts data from those packets and deliver to the application layer. Now let's see what changes would have to be made when we make the changes to our assumptions. Now let us first understand what are the implications of bit level errors. Now if errors happen in the data being transmitted, that means that data is unusable. Whatever data was sent from the sender, certain errors took place while transmitting and the receiver received a corrupt data. So when data error take place, the receiver has no use of the data. But remember, we are developing a protocol which is a reliable protocol. That means the transport layer is guaranteeing to the sender that the data it is receiving from the application layer would be reliably delivered at the other end. Now if data error takes place, that guarantee becomes meaningless. But because it has given a guarantee, it should now ensure that even if error takes place, then somehow it should ensure that the receiver receives the correct data. Now how it can be done? Can you think for a moment and give a solution to this problem? The only way of solving this problem is retransmission of those data which were corrupted. That means the sender would retransmit the data again until and unless that particular data is reliably delivered to the other end. But how does the sender know that the data got corrupted in between? The sender simply sends its data. If it got corrupted, there is no way that the sender knows whether the data got corrupted or not. So there are two major issues now. First issue is, how does the receiver know that the data got corrupted? The second issue is, how does the sender know that the data got corrupted? Only if it knows that the data got corrupted in between, then only it can retransmit data. But first, it should know that the data got corrupted. And even before that, the first question is, how does the receiver know that the data got corrupted in between? Now let us handle the first question. How does the receiver knows that the data it received got corrupted or not? If you have followed the lectures on UDP, then the solution should be easy. You might have remembered that there was a field known as checksum, which is used for error detection in UDP. The same techniques is used here as well. So the essentially the solution is that the sender, apart from the data, would also send some extra information known as checksum. This checksum is calculated by a certain technique which we have already discussed during our discussion of UDP. So this extra information helps the receiver to understand whether the data is received correctly or some error has taken place. Now let's handle the second question. Say that the receiver has received a packet which got corrupt in between. So essentially the sender now should retransmit the packet so that the receiver received the correct packet. But how does the sender know that the receiver received a wrong packet in the first place? It can only know that only if the receiver informs the sender that it received a corrupt packet. The receiver has already calculated the checksum and understood that it has received a corrupt packet. Now it should inform the original sender that I have received a corrupt packet, so retransmit that packet. If the sender received that information, then it can retransmit the packet. So now there is some form of acknowledgement. So let's introduce two different types of acknowledgement. Say one is known as a positive acknowledgement and one is known as a negative acknowledgement. The positive acknowledgement says that a sender sends data, it is correctly received, the receiver sends a positive acknowledgement that I have received the correct data, now you can proceed with the next data. Now if it sends a negative acknowledgement, then the sender understands that the packet it sent did not arrive at the receiver correctly, so it should retransmit that packet once again so that the receiver receives the correct data. So let us see what changes are required to be made to our protocol. Let's see for the sender side first. Let's remove the receiver side as of now and see what changes are to be made at the sender side. So at the sender side, we'll always listen for data to come from the application layer. Now if data arrives from the application layer, the transport layer will divide the data into smaller packets. Now this time it will also include the checksum. Why does it include the checksum? To ensure that the receiver understands whether it has received correct data or not. So this make packet includes a checksum. Now this is important. This is the first change that has happened in our protocol. Once it makes a packet with a checksum, it delivers those packets to the network layer to be delivered at the other end. Now let's see what changes are to be made at the other end, the receiver side. Now let's see at the other end, the receiver side. At the receiver side, the transport layer is waiting for data to come from the network layer. Now if a packet arrives, now this is important. Now if a packet arrives, first it calculates the checksum. Now this is important because if a wrong packet arrives, then that packet is meaningless. So first it calculates the checksum. If the checksum is valid, if the checksum is valid, what's the meaning of it? It means it has received a correct packet, then it can extract the data from the packets and then deliver the data to the application layer. But apart from that, it will do one more extra thing. It will also send a positive acknowledgement to the other side, the sender, saying that I have received a correct packet. Why does it send? Because Only if the sender understands that a correct packet has received, then only the subsequent data can be sent. So one more extra step is added. The extra step is send a packet. What is this packet? This is a positive acknowledgement. This is a positive acknowledgement. Let's name it ACK. This is normally written as ACK. So it sends a packet which is a positive acknowledgement to the sender. So this is the first step. What is the first step? That the transport layer of the receiver side receives a packet. It first checks the checksum. If the checksum is valid, then extract the data from these packets and deliver the data to the application layer, because a correct packet has been received. Apart from that, it sends a positive acknowledgement to the sender saying that I have received a correct packet. But what if it has received a corrupt packet? Now, if it receives a corrupt packet, then the checksum would be invalid. So let's see what happens. If the checksum is invalid, that means it has calculated the checksum and found that certain errors have taken place. Now what it should do? It should inform the sender that it has received a corrupt packet. So simply send a packet. Now this packet is a negative acknowledgement. Negative acknowledgement. Now this negative acknowledgement is normally written as NAK. So if the checksum is invalid, it will send a packet to the sender saying that it has received an incorrect packet. This packet is known as a negative acknowledgement, and because it is an incorrect packet, certain errors have taken place. It would not follow this step of extracting the data from the packets, because this data is meaningless. So if the checksum is invalid, it will simply send a negative acknowledgement to the sender saying that it should now retransmit the data. Now let us go back to the sender side. Now remember, some more extra work has to be done by the sender now. Till now we have seen that if data arrives from the application layer, transport layer will divide the data in packets, which includes a checksum, and then deliver the packets to the network layer. Now remember, now if data arrives from the network layer, now why do we think I have added this part? Now remember, this part is when it is getting data from the application layer. Now it can get data from the network layer. So what data it can get? It can get data from the other end. It has sent some data to the other end. Now that other end has sent an acknowledgement. Now this acknowledgement would obviously arrive from the other end, the network layer. Now if data arrives from the network layer, it will see whether it is a positive acknowledgement or it is a negative acknowledgement. Now remember, if it is a positive acknowledgement, then it is easy, then it can start transmitting more data, more packets. But if it is a negative acknowledgement, then it has to retransmit the original data. So now this is important. If data arrives from the network layer and that data and that packet is a negative acknowledgement, what it will do? It will then retransmits the packet. Which packet? The previous packet. The packet it previously sent. Now remember, now here comes a concept of buffering a packet. So a sender has to buffer or store the packet unless and until it got the confirmation from the other end that the packet has been delivered correctly. So if that packet is not delivered correctly, if some error has taken place, that means it has to retransmit the packet. So it has to keep that packet at its buffer for a particular amount of time unless and until that packet is correctly delivered. So what changes has been made at the sender side? The sender side is that if it receives a negative acknowledgement, it retransmits the packet so that the correct data can be delivered to the other end. Now this is the finite state machine of our RDT version 2 of the sender side. Please refer to your textbook of Ross and Kurose for this FSM. This FSM should be very easy to understand now. What is happening in the sender side? It is waiting for call from above. Again, above means the application layer. So whenever data comes from the application layer using this function, it makes a packet with the data and it also includes a checksum, and then it sends the data to the network layer. After sending the data, it will wait for either a positive acknowledgement or a negative acknowledgement. Now if it receives a packet, from the network layer, which is a negative acknowledgement, it again sends the packet. And if it receives a packet which is a positive acknowledgement, then it go back waiting for data from the application layer so that it can deliver subsequent data to the other side or the receiver. So take a moment to see this finite state machine and ensure that you have understood all these different functions. And this is the finite state machine of the receiver side. Again, it is waiting for call from below, means it is waiting for data to come from the network layer. Now if it receives a packet and it is a caught-up packet, how does it know it's a caught-up packet? By checking the checksum. If the checksum is valid, that means it understands that it has received a caught-up packet. Then what it will do, it will make a negative acknowledgement packet, a packet which says that I have received a caught-up packet, and send this negative acknowledgement to the original sender. Now if it receives a packet and that packet is not caught up, that means it has received a correct packet. What it will do, it will extract the data from that packet and deliver to the data to the application layer because it has received a correct packet, and also it will make a positive acknowledgement and send the positive acknowledgement to the sender. If you have understood the previous discussion, this finite state machine is fairly easy to understand. Again, please refer to your textbooks to understand this FSM in more detail. Now, there is something which is missing in this modified version of RDT, the RDT version 2. Can you think what is missing? What we have done till now is the sender receives data from the application layer, makes a packet which includes the checksum and sends to the other side. The other side calculates the checksum. If it is a positive, it is a correct packet, it sends a positive acknowledgement. If it's a incorrect packet, it sends a negative acknowledgement. The sender, if it receives a negative acknowledgement, then it retransmits the packet. This is what is happening in this. Now, a big part is missing in the sense that error can also take place in the acknowledgement that is coming from the receiver end. That means the receiver, when it receives a packet and it found that the packet has either correctly or incorrectly arrived, it is sending a acknowledgement, either a positive or a negative one. Now when it is sending the positive or negative acknowledgement, then that acknowledgement can also get caught up. Now again, two questions can arise. First question, how does the sender know that the acknowledgement, whether positive or negative, it has received is a correct message or an incorrect message? Now the solution to this question is fairly easy. It's simple. You simply need to add a checksum to what? To the positive or negative acknowledgement. That means the receiver, when it sends a positive or negative acknowledgement, it sends a checksum with it. So let's make a change immediately here. So when it sends a positive acknowledgement, say positive acknowledgement with checksum, and when it sends a negative acknowledgement, it also sends the negative acknowledgement with checksum. That means just like the sender sends its data packet with a checksum, the receiver also sends its positive or negative acknowledgement with a checksum, so that when the original sender receives an acknowledgement, it understands whether the acknowledgement it has received is correctly received or incorrectly received. But the second question is more typical. If the receiver receives an acknowledgement which is corrupted, how does it know that whether it is a positive acknowledgement or a negative acknowledgement? If it does not know whether it's a positive or negative acknowledgement, then what it should do now? Now this is a very, very typical problem. A naive solution would be something like this. The sender, when it receives an acknowledgement which is corrupted, it again asks the receiver that I received the acknowledgement incorrectly. I don't know whether it's a positive or negative acknowledgement. Can you send me that again? But again, when it sends this message, that message also get corrupted. When the receiver sends a subsequent positive or negative acknowledgement, it can also get corrupted. So this solution, this naive solution, cannot work. So it should follow some other solution. The solution that is followed in networking is fairly simple. Whenever a machine receives an acknowledgement which got corrupted in between, that means the receiver does not know whether it's a positive acknowledgement or a negative acknowledgement, then the solution it follows is that irrespective of whether it's a positive or negative acknowledgement, it retransmits the original packet once again. That means if the original acknowledgement is a negative acknowledgement, then anyhow it had to send that packet again, retransmission. In that case, it would not matter. But if it was a positive acknowledgement and then the acknowledgement it received got corrupted and it has no way of knowing whether it is a positive acknowledgement or a negative acknowledgement, then it would retransmit that packet again. Now this creates a new problem. Can you think what that problem could be? So let us see what is the problem. Say a machine A sends some packet to machine B. So A sends a data packet to B, and with the data packet it includes a checksum. This part we have discussed. Machine B receives the packet, it checks the checksum and it found that its checksum is correct. That means it has received the packet correctly. So it sends back a positive acknowledgement. Positive acknowledgement, it says that I have received the correct packet, and with this positive acknowledgement it also sends its checksum, because error can take place in this acknowledgement also. Now say due to some problem in the transmission link, this acknowledgement message got corrupted. So A received a acknowledgement which is corrupt. So it does not understand whether it is a positive acknowledgement or it is a negative acknowledgement. So going by the previous principle, if A receives an acknowledgement which is corrupt, it retransmit the original packet. The packet it transmitted here, it retransmit that original packet again. Now when B receives this packet again, there is no way of knowing is it a new packet or it is a retransmission of the old packet, because there is no way of distinguishing between these two packets, and this creates a new problem. This problem is solved in networking by using a concept known as a sequence number. So along with the checksum, now whenever A sends a packet to B, it also inserts something known as a sequence number. So in this step, whenever A retransmits a packet due to receiving an corrupt acknowledgement message, then B can see the sequence number and understand that it is a retransmission of a previous packet. So even if it had received that packet correctly in a previous instance, it can simply discard the retransmitted packet just by looking at the sequence number. So how many sequence number do we require in our protocol? Satisfy yourself that we require only 2 sequence number. A single bit sequence number that can distinguish between 2 different packets. Let us see how. Say we use only 2 sequence numbers. The sequence numbers are 0 and 1. Say A sends a packet first and the sequence number is 0, and now it is waiting for the either a positive or negative acknowledgement. If B received the corrupt packet from A, then it sends a negative acknowledgement, then A retransmits the 0th number packet again. Say B sends an acknowledgement and that acknowledgement got corrupted. So A retransmits the packet 0 again, but if B had previously received packet 0 correctly, this retransmission won't create any problem, because B can simply discard this packet as a retransmission. Now if B sends a positive acknowledgement and this positive acknowledgement is received correctly, now A can send a separate packet with a sequence number 1. Now when this packet 1 arrives at B and B sends a positive acknowledgement, now A can reuse this sequence number 0 again, because that 0 was used previously. Now 0 will indicate a new packet. So 2 sequence numbers are sufficient to distinguish between the different data packets. Now we can make necessary changes in our protocol also. So in the sender side, including with the checksum, now we have something known as a sequence number. Now remember, this sequence number alternates between 0 and 1. So if data comes from the application layer, it will divide the data into smaller packet and it will put a checksum in a sequence number and send the data to the other side through the network layer. Now whenever an acknowledgement comes from the network layer, if the packet is a negative acknowledgement, it obviously retransmit the packet of that particular sequence number. It also retransmit the packet if it receives a corrupt acknowledgement. That means it does not know whether it's a positive or negative acknowledgement. So it retransmit in two cases: if that packet is a negative acknowledgement, or if it receives a corrupt acknowledgement. Now, if it receives a positive acknowledgement, obviously it can. So let's put another thing here. So, and if the packet is a positive acknowledgement and it is not corrupt, then go back to step, say, 1. So what is step 1? This is step 1. So this is step 1. That means it goes back to waiting for data to come from the application layer. Now remember, this sequence number alternates between 0 and 1. So one time if it sends packet number 0, then next time it will second packet number 1. Again next time it will second packet number 0. So this will alternate between these two sequence numbers. And we make some necessary changes in the receiver side also. So when a packet arrives, apart from the checksum, it also checks the sequence number, and if the sequence number is valid and the sequence number is also valid. What's the meaning of sequence number is valid? That means if it is waiting for a packet with sequence number 0, it should receive a packet with sequence number 0, not a packet with sequence number 1. So if the checksum and sequence number both are valid, then it will obviously extract the data from the packets and deliver it to the application layer, and also then sends a positive acknowledgement to the sender back. And when the checksum is invalid, then obviously it will send a negative acknowledgement. Because we have made certain changes to our protocol, let's rename this protocol as rdt 2.1 instead of 2.0. let's rename it as 2.1. same with the sender side also. Let's rename it 2.1. we have changed the version number from 2.0 to 2.1 because we have introduced a new concept, and this new concept is a sequence number. And now let's check the finite state machines of rdt 2.1 for both the sender and receiver. Again, these finite state machines have been taken from your textbook of Ross and Kurose, because this may not be very clear in this slide. So I urge you to refer to your textbook. If you have followed the discussion till now, these finite state machines should not be difficult for you to understand. So this is the sender side. So there are two sequence numbers, 0 and 1. So most of the functions are replicating for both this sequence number. So just for a very quick look at this FSM, so it is waiting for data to come from the application layer. Now it's for sequence number 0. Whenever data arrives, it makes a packet that includes the checksum as well as the sequence number. Once it sends this packet over the network layer, then it waits for an acknowledgement or a negative acknowledgement for that particular packet with sequence number 0. When it receives a corrupt packet, corrupt packet means it receives a corrupt acknowledgement, then again it retransmits the packet. Remember, we have discussed this very clearly. If it receives a corrupt acknowledgement, it retransmits the packet again. Now if it receives a acknowledgement which is not corrupt and it is the correct acknowledgement number, then it goes for waiting state. It waits for data to come from the application layer, and if data arrives this time the sequence number would be 1. So this state and this state would be similar, this state and this state will be similar, this state and this state will be similar. The only difference is that the sequence numbers are different. And this is the finite state machine of the receiver side. So at one time it will wait for packet number 0, at the other time it will wait for a packet with sequence number 1. When it receives a packet which is not corrupt and it has got the correct sequence number, then obviously it will follow all the steps of extracting data and delivering the data to the application layer. And after delivering the data from the application layer, it will wait for the next sequence number. Now if it receives a packet which is corrupt, that means it checked this checksum and it found that the packet got corrupted. Then what it will do, it will make a negative acknowledgement and send it to the sender. So if we follow the discussions, then obviously this finite state machine should not be difficult for you. But take your time and go through these finite state machines. Now there is some terminology which you should be aware of. A stop-in with protocol is a protocol in which the sender sends one packet and waits for the receiver to acknowledge it, and when it receives the acknowledgement, then it will send the subsequent packet. Because the protocol RDT which we have been discussing exactly behaves like this, so the protocol RDT can be said to be a stop-in wait protocol. We have made a fairly stable version of the RDT protocol, but we can still fine-tune or optimize the rdt 2.1. Now the optimization we want to make is that we want to eliminate the negative acknowledgement. We are using two types of acknowledgement. One is positive acknowledgement and one is negative acknowledgement. Instead of having two different types of acknowledgement, we want to use only one single type of acknowledgement, and this is actually done in networking. So instead of having a positive acknowledgement and negative acknowledgement, the concept we use is that whenever we receive a incorrect packet, a packet which is corrupt, instead of sending a negative acknowledgement, what the receiver does, it sends a positive acknowledgement for a previously received packet. That means, say the receiver first correctly received packet number 0. Now it is waiting for packet number 1. Now it receives a packet, but the packet got corrupt. What happened in the negative acknowledgement, that whenever it receives a corrupt packet, it sends a negative acknowledgement. Now instead of sending a negative acknowledgement for that packet, what it does is it sends an acknowledgement for the previously correctly received packet. That means previously it received correctly packet number 0. Now it sends an acknowledgement for packet number 0. Now the sender previously received an acknowledgement for packet number 0. Now when it receives an acknowledgement for packet number 0 again, that means it receives two acknowledgement with the same sequence number, then it understands that the packet which is recently sent, certain errors took place in between transmission, so it again retransmits that particular packet. That means using a duplicate acknowledgement, acknowledgement with the same sequence number is same as sending a negative acknowledgement. Let us name this modified version or this optimized version as rdt 2.2. Here we have made a minor change. The minor change is replacing a negative acknowledgement with a positive acknowledgement message. You can see the changes here. So it is waiting, say this is waiting for an acknowledgement for the packet number 0. So if it receives an acknowledgement with of packet number 1, that means instead of receiving a negative acknowledgement, it is receiving a positive acknowledgement, but the positive acknowledgement is for packet number 1. It was waiting for the acknowledgement for packet number 0, but instead it has received an acknowledgement for packet number 1. That means it has received it in duplicate. It has previously received in this state, the previous state when it was waiting for acknowledgement 1, but it has received this acknowledgement when it is waiting for the acknowledgement of packet number 0. So in this state it understands that the packet with sequence number 0 was received incorrectly, so it will retransmit the packet with sequence number 0. And this is the finite state machine of the receiver side for rdt 2.2. Again, you can see that instead of NAK, we have used the concept of using positive acknowledgement for a previously correctly received packet. So if it is waiting for the packet with sequence number 1, if it receives a corrupt packet, what it does is that it creates a positive acknowledgement with sequence number 0 instead of acknowledgement with sequence number 1, because the concept is that when it receives an incorrect packet, a corrupt packet, it will send an acknowledgement for a packet that was received correctly previously. That means if it is for waiting for 1, it will, and it receives a corrupt packet, it will send an acknowledgement for packet number 0 instead of packet number 1. So that's it for today. So we have created the version 2 of our reliable data transfer protocol. The subsequent lecture will introduce the final assumptions where, apart from bit level errors, packet can also get lost, and then we can actually reach to a level where we can understand how TCP actually works. Again, for more elaborate discussion, do refer back to your textbook, the textbook by Kurose and Ross. Thank you.